I now call to order the Society's 2,509th meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's meeting and the lecture by Mike Falkowski and Mike Seablom. First, let's thank our sponsors. Society is grateful to PSW full-year series sponsor, PSW member Mike Helton and Helton Associates, LLC. Thank you, Mike. And we're grateful to current series sponsor, PSW member Joe Schulman. Thank you, Joe. And finally, we're grateful to the sponsor of tonight's lecture, PSW member Frederica Darema. Thank you, Frederica. We also have to give Frederica credit for inspiring me or cajoling me, take your pick, into inviting Mike and Mike to speak tonight. I think you'll see that was a very good choice on her part. I'm very pleased to say that PSW did receive over $10,000 in donations that were qualified for the 2-to-1 match. And so we have taken in $30,000 in total, which helps a lot with meeting our budget and ending the year in the black. Society is very grateful to all donors who contributed during this period, and in fact, to donors who contribute during any period, but particularly this period, and especially to our match donor who asked that we not name him. So please, a round of applause for that. I'm pleased to announce the following new members. John Arrowwood, Director of Research at NICE Systems, spelled all caps, N-I-C-E, interested in speech and audio technologies and large language models, who learned a PSW from YouTube. Eric Smith, Associate Director for Research, the Astrophysics Division at NASA, interested in astronomy, astrophysics, space missions, and planetary science, who was a PSW speaker and learned of the Society from our invitation to him to speak way back then. Jason Eckberg, an officer with the United States Air Force, broadly interested in the sciences, particularly aeronautical and electrical engineering, computer science, and AI, who learned a PSW from PSW member Robin Taylor. Jason actually is / was a speaker member, but he generously decided to pay dues as well. So thank you, Jason. And tonight's speakers, Mike Falkowski and Mike Seablom, who learned a PSW from our invitation to them to speak tonight and whose interest will be clear in some small part from their lectures. And we welcome them all to membership. If you're interested in becoming a member of PSW, you can access a membership application on the PSW website by clicking the blue Join button on the upper right-hand corner of the homepage. And if you're here in the Powell Auditorium, you can take one of the business cards at the back and use the QR code to access the application form pretty directly. You can also use the QR code to find out more about PSW. Everyone with a genuine interest in science and a willingness to pay the $75 annual dues is welcome to join. Recording Secretary Scott Matthews will now present the minutes of the 2,508th meeting and the lecture by Scott Woke on highlights of the X-ray universe, 25 years of Chandra, and more to come.
Good evening, everyone. On January 24th, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined the other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2508th meeting of the Society to order at 8:02 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Javier Garay titled Fusion Energy Meeting the Engineering Challenges. The minutes were approved pending a minor correction. President Milstein then introduced the speaker for the evening, Scott Wolk, of the Harvard-Smithsonian Chandra X-ray Center. His lecture was titled Highlights of the X-ray Universe, Chandra's 25 Years of Observation and More to Come. The speaker began by describing the size of the Chandra spacecraft, approximately the size of the Powell Auditorium. He indicated that most X-rays do not penetrate the Earth's atmosphere and must be observed from space. Wolk described the operating principle of an X-ray telescope, which uses specialized mirrors to reflect the X-rays at a glancing angle and thereby focus them on a detector. He showed images of the precise polishing and alignment procedures used to fabricate and assemble Chandra's X-ray optics. Wolk described the two X-ray detectors, a microchannel plate, which provides high spatial resolution but no spectral information, and the ASIS camera, a CCD device that provides energy sensitivity as well as images. He claimed that the X-ray background of these detectors is so low that they average 2 counts per pixel per 1 million seconds of integration time. He showed a video of Chandra being deployed from the cargo bay of Shuttle Columbia in 1999. He described the use of Chandra's onboard rockets to move the observatory from low Earth orbit to its final orbit, where, although it cannot be reached for servicing, it can stare at celestial objects for several days uninterrupted. Wolk showed spectrally separated images from a supernova remnant, identifying specific elements from their characteristic X-rays. He described the 4 main sources which produce celestial X-rays: shock waves in plasma, synchrotron radiation, accretion energy, and supernova remnants. He indicated that X-rays are emitted by, quote, nearly everything in astronomy, end quote. The speaker presented what he called the 3 pillars of the, quote, Pathways of Discovery, the 2020 Decadal Survey for Astronomy and Cosmology. These were worlds and suns in context, the nature of extreme cosmic events, and cosmic ecosystems. Wolk began with cosmic ecosystems, which he described as understanding the evolution and interaction of galaxies. The speaker discussed the role of dark matter in cosmic evolution. He compared images from Chandra and Hubble, showing how the collision of 2 galaxies created dramatic differences in the distribution of normal matter and dark matter. He discussed how observations from Chandra allowed a more accurate determination of the dark energy constant of the universe. The speaker then discussed extreme cosmic events. He showed images of the collision between 2 neutron stars, which created gravity waves that were detected by LIGO in 2017. He said that 2 days after the event was observed by LIGO, Chandra observed no X-rays. However, 9 days later, the X-ray source was clearly visible. He discussed possible mechanisms to explain the delay in the observation. He showed an X-ray image of supernova remnants, including type 1A and type 2, or core collapse supernova. He showed how data from Chandra can be used to map out the distribution of various elements in the supernova remnants. Finally, Wolk discussed worlds and suns in context. He explained that Chandra images have provided key insights into star formation and stellar evolution. As examples, he showed images of the Carina Nebula, the Lobster Eye Nebula, and the Orion Nebula, all star-forming regions. He described the use of Chandra's high-resolution spectral sensor to measure both the composition and the Doppler broadening in 36 young, hot stars in the Orion Nebula. The speaker then described the use of Chandra for finding and studying exoplanets. Wolk ended his talk by presenting a video produced in collaboration with the Perkins School for the Blind, where Chandra images were used to synthesize the accompanying audio track, saying that science should not be limited to sighted people. The lecture was followed by a question and answer session. A member asked if there were plans for using coated aperture imaging or diffractive optics for X-ray telescopes. Wolk responded by saying that each of these approaches provided some advantages and disadvantages and were therefore complementary. He said that these particular techniques are not employed on Chandra, but they are used in a number of other instruments. A member asked, quote, "What are you finding about exoplanets?" End quote. Wolk responded, "Exoplanets are difficult," saying that many exoplanets turn out to be barren rocks. He indicated that the James Webb Space Telescope had been crucial in these observations. He discussed the details of how energetic X-rays from the host star can strip away the atmosphere of a nearby planet, but that exoplanets orbiting M-class stars were more likely to retain a thick atmosphere. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,508th meeting of the Society at 10:05 p.m. Eastern Time. Temperature in Washington, D.C., minus 0.5 Celsius. Weather, cloudy. Audience in the Powell Auditorium, 60. Viewers on the live stream, 40, for a total of 100 live viewers. Views of the video in the first 2 weeks, 772. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Are there any comments on the minutes? Are there any corrections or additions? If there are none, I will entertain a motion to accept the minutes as read. A second. All members in favor? All members opposed? Minutes are accepted unanimously, subject to the proviso that those of you who are online and have any reservations or comments can submit them directly to the corresponding secretary at correspondingsec@pswscience.org. And if necessary, we will correct or amend the minutes. Otherwise, they are accepted as read and will be posted to the website in due course. We now turn to tonight's lecture by Mike Seablom and Mike Falkowski. Mike Seablom is the Associate Director for Technology and NASA's Earth Science Division at NASA headquarters. He manages a portfolio of programs that invest in the next generation of Earth science missions. Previously, he was Chief Technologist for NASA's Science Mission Directorate, with responsibilities for surveying and assessing technology needs for the heliophysics, astrophysics, earth science, and planetary science divisions. He's a meteorologist by training. He began his career applying estimation theory to data assimilation for numerical weather prediction and developed one of the first parallel implementations of this approach. Mike earned an MS in meteorology at Florida State University, an MS in atmospheric science at Purdue, and an MBA in the management of technology at Georgia Tech. Mike Falkowski is the program manager of the NASA Wildland-Fire program at NASA headquarters in Washington, D.C., where he focuses on facilitating the development of wildland fire technology and research and related applications. Before joining NASA, Mike was professor of ecosystem science and sustainability at Colorado State University and conducted research on ecosystem science and management. And before that, he held faculty positions at the University of Minnesota and Michigan Technological University. And he was also a Natural Sciences and Engineering Research Council of Canada Research Fellow with the Canadian Foreign Service at the Pacific Forestry Center in Victoria, British Columbia. Notably, before he began his academic career, Mike served on wildfire fire crews, gaining hands-on experience with managing fires and with the communities that work on the ground in fire management. Mike earned an MS and PhD in forestry at the University of Idaho. All questions will be fielded during the question and answer period after both lectures with our two speakers on stage. Mike Seablom, I believe you begin. The stage is yours.
Good evening. Thank you for inviting Mike and I tonight. We're very happy to be here. We're going to do this in two parts. I'm going to start off by telling you a little bit about how we invest in technology in the Earth Science Division at NASA headquarters. And then Mike is going to fill you in on our latest projects, our latest programs that are investing in wildfire technology and research in our new Fire Sense program that is designed to take NASA Earth observing capabilities and bring them to bear on the for use by the operational wildfire communities or agencies. Okay, so I lead a group of program officers in the Earth Science Division who are tasked with investing in new technologies for future missions. The goal is really to make those missions more capable and affordable, which is a growing concern for moving forward. But the goal is really to expand our knowledge of Earth system science. Our vision, the Earth Science Division, a thriving world driven by trusted, actionable science. And compelled, our mission is really looking at acknowledging the planet's rapid change and determining how we can innovate and collaborate to better understand the Earth as a complete system. So one example of that is, the long-term monitoring of the Earth is critically important. This is an image, this is a time lapse of the minimum Earth Arctic sea ice going back to 1975. And you can see over the decades, the ice pack in the summer has been shrinking, about 13% ice loss per decade. The what it takes to put a record like this together involves bringing together observations from spaceborne instruments, from sea level surface instruments, performing the analysis to make sure there's consistency, to perform calibration rather, to make sure that the result is consistent over a long period of time. What we're seeing here is the Arctic sea ice in the summer could be completely gone by 2040. This results in a number of economic opportunities for the nations that border the Arctic Ocean: Russia, Canada, the U.S., Denmark, Norway, and Iceland. But there are also risks. There's a good story in Al Jazeera about how Russia's 24,000 kilometer border is now exposed, and they realize this is a risk. And they're reopening a number of the previously dormant Soviet military outposts that existed in the Arctic. So monitoring of the Earth over a long period of time is critically important for a number of reasons. Our Earth Science Division is divided into elements. We have our flight element, which develops and launches our fleet of satellites, and also the data systems that are involved in bringing the information to the ground, and also to allow us to perform analysis on the data. Research and analysis is our critically important piece that takes the data and turns it into knowledge and information. Earth Action is our newest element. This is a new initiative in the Earth Science Division, which is Earth Science to Action. The goal is really to take the information that we're receiving and apply it to the problems that U.S. citizens are facing. So this is kind of like taking the old applied sciences program and expanding it. And the Wildfire Initiative is part of our earth science to action element. And then finally, technology. And this is where we invest in the capabilities for future missions. It's not only the instruments, it's also the information systems so that we can enable the other elements. And the way this is set up, the technology element is not, we don't report directly to any of the other elements. We report directly to our director, Karen St. Germain. So we treat the other elements as customers of what we do, but we do not, we're not reporting directly to them. And any large business that has an R&A component, a research and development element, this is really what you want to do to keep the innovation protected. Here's a mapping of our current fleet of Earth observation satellites. It starts from the innermost point. Let me see if I can get this to work. The innermost ring represents our oldest satellites that date back to the turn of the century. Terra, Aqua, and Aura are from the original Earth observing system fleet. And then as it goes out, these are more recent satellites that measure very different aspects of the Earth system. And I'll point out just a few of these. I'll go into more detail on SWAT, which was launched just 2 years ago, PACE, which was launched last February, and we'll also look at GRACE and what we're looking for in the future as we go beyond these missions. What you see, the CubeSats represent, let's see, on the right, these satellites represent the technology demonstrations that my element is investing in. These are all small satellites that are designed to retire the risk of the instruments when they're used in a major mission. The INVEST program is very important because it allows those instruments a fighting chance in the AO competition because we take the technology readiness up to level 6 so that they're ready for use on a mission. So here's an example of, like I said, the PACE mission. This is the Plankton Aerosol Cloud Ecosystem mission that was launched last year. What we're seeing in the Aegean Sea and the Black Sea, you're actually seeing the blue and the green. This is phytoplankton, which is a product of our ocean color instrument that was developed with our technology office investments. And then over in the Aegean Sea, you're seeing aerosols, which is detected from a different instrument on the spacecraft. This is from our hyperangular rainbow polarimeter, which is looking at clouds and aerosols. This mission is, the ocean color instrument is the first implementation of a hyperspectral ocean color instrument. This is important because we can distinguish between various features. What you're seeing here is the aftermath of Hurricane Helene back in September off the coast of Florida. The image on the left, this is the pre-Helene environment, and the image on the right is what happened after. You're seeing the upwelling of sediment, but also plankton off the west coast of Florida. The fact that we now have a hyperspectral instrument allows ocean scientists to distinguish between the sediment and the plankton. And the plankton, by the way, the phytoplankton account for a very important part of our carbon cycle. Carbon dioxide from the atmosphere is absorbed. They release oxygen. As much as 50% of the oxygen of the planet is coming from the phytoplankton. So understanding the health of the phytoplankton And, and to be able to distinguish between the different types of phytoplankton is critically important. Another mission that we have is SWAT. SWAT provides detailed measurements of the water elevations across various global water bodies, not just the ocean, but the inland waters as well. And unfortunately, we were having trouble getting this video to play. I see somebody's giving it a try. Oh, okay, maybe it will work. Well, while we're trying that, the data gathered is going to enhance our understanding of small-scale ocean circulations, the ocean's role in climate, the hydrological cycle, and freshwater management worldwide. So for the first time, we get large swaths of the height of the ocean surface, but also of the inland waterways as well, which you can see on the map. All right. And now it's not, oh, there we go. Okay. So our strategy for investing in new technology is to rely on the competitive peer review process. We provide active management of the technology projects, which means that we don't just give out grants, we follow the technology through the development process. We have our program officers are following the deliverables, and failure or to have to change the approach is an option. Unlike the fever charts of our flight missions, which we always hope will be green, in our technology program, we expect some fall colors. We expect yellows and reds because this is a program where we take risks and we try to invest in new types of techniques. The program officers are there to help re-vector the activities when things don't go according to plan, or if necessary, we will stop the activities completely. We do expect to have a small number of failures in the course of the program, but this is really designed to retire risk in the portfolios. We have about 6 different programs. We have an instrument incubator program, which is for the large scale, complete instruments, and then we have a component program to complete the observation technologies. We also have an intelligent systems program that is involved with advanced modeling techniques and also advanced information systems technologies, which include things like quantum computing, neuromorphic computing, artificial intelligence and machine learning, which is now being used quite a bit. So let's take a look at the process for how these go from concept to a final mission. So we'll start with PACE. Like I said, this is a mission that combines an ocean color instrument and the hyperangular rainbow polarimeter. So these are 2 separate instruments that were invested by ESTO over a long period of time. So going back to, and this is an image of what the different types of plankton look like, and also what the polarimeter can see from space. This started back in 2008. Its origins began with this mission called ORCA, an instrument called ORCA, the Ocean Radiometer for Carbon Assessment. It was, the PI was Chuck McLean at Goddard Space Flight Center. He and his team took the technologies from previous ocean color missions, including the Coastal Zone Color Scanner from Nimbus 7, and also the CWIFS instrument, and used a lot of the incremental technology investments over time to miniaturize those components. So not only to get the better capability, the cost reductions we need reductions in size, weight, and power. And so he was able to do this with the technology investments. The real key the breakthrough was the ability to have a telescope that could rotate at precisely 5.7 revolutions per second, synchronized perfectly with a charge coupled device. And that resulted in the world's first hyperspectral ocean color instrument, which gives us the different types of plankton and gives us a much better insight into how the health of the plankton, the amount of plankton that are coming up to the surface. There is some concern with the temperature stratification of the oceans that there may be less upwelling. This gives us our ability to better analyze and process and understand how that's changing. So for the polarimeter, HARP-2 is the polarimeter on PACE. HARP-1 was the technology demonstration mission. And this also started from a previous mission, which started really with the MISR instrument on Terra. Vandelay Martin was the PI at University of Maryland, Baltimore County, was able to use miniaturization to create a polarimeter that was, instead of 150 kilograms, which is what we had before, was able to reduce it to 10 kilograms. And then widen the field of view from 70 degrees to 114. So those technology developments occurred over about a 10-year period beginning in 2013. Okay, SWAT was the other mission that I mentioned. So SWAT began even farther back. So SWAT started back in 1998 with Li Long Fu, who first proposed the ability for a Ka-band synthetic aperture radar to measure a wide swath of the ocean surface. Previously, we could just do point measurements of the ocean surface. So this proposal first came in 1998. There were two key projects that allowed the multi-frequency antenna to be developed, and this eventually became the key points of the SWAT mission. More was needed in 2008 and 2010. We had two other investigators, Mark Thompson and Greg Agnes, also at JPL, were working out the structural components that would eventually become the SWAT antennas, and the technology was needed to make them structurally flat and thermally stable in order to meet the very precise precision requirements. And then Paul Sequeira at the University of Massachusetts developed a low power, high bandwidth Ka-band receiver, which was capable of precision measurements over a wide bandwidth, which was a key challenge for the SWAT mission concept. And also there was a dual down converter that was needed to be developed around the same time. And then finally, we developed an airborne version that allowed us the first ever airborne Ka-band synthetic aperture radar interferometer, which was flown for the better part of a decade to refine the design of the spaceborne mission. And it's also now used to validate our SWAT data. So SWAT was a breakthrough technology. It was the first time we had wide swath measurements, not only of the ocean, but of terrestrial water. And it took the better part of, from 1998 all the way to about 2006, 2008, to retire the risk completely. So the investments take a while, and that's an example of how we develop the technology over time. So looking forward, our portfolio includes lasers, which are used for aerosols, clouds, chemistry, 3D winds, and mass change. Passive microwave, this has come a long way in the past decade for snow characterization, atmospheric composition, and soil moisture. Passive optics are used for ecosystems, cloud and land surface characterization, and then radars for a lot of things, like going from soil moisture all the way to, like I said, the surface water topography. So those are kind of the classical technologies that are being developed for mission enabling. In terms of emerging or breakthrough technologies, we're looking at things like quantum sensing, digital twin architectures, freeform optics, spaceborne deployable antennas, metamaterials, and then novel observing strategies, where we're using multiple spacecraft coupled with numerical models to make targeted observations. And then our portfolio is really designed to be about 70% mission enabling, 20% enhancing, and then 10% in the transformational part. You could probably do an entire evening talking about any one of these new emerging technologies. Quantum sensing is a big one that's coming up. We've had, you could say, lasers or quantum sensors, or but what we're really talking about here is a new generation of quantum sensing that involves superposition and entanglement using properties of quantum particles. And this can be used not only in earth science, but in astrophysics and planetary science as well. So this is a whole emerging area. Now, at NASA, we don't typically invest in basic research. So we have a partnership with our Space Technology Mission Directorate. We have a Quantum Sensing Institute that has been set up at the University of Texas, Austin, that are looking at applications, new types of applications where quantum sensing could be used in Earth science in the next decade. So this is ongoing. But in the next 10 or 20 years, this could be a step function in our ability to measure, to make measurements at much higher precision. So one example that we have, if we go back to GRACE, so GRACE is a mission that was first launched in 2002. It's designed to measure mass variability, changes due to surface and deep currents in the ocean, runoff, groundwater storage, very important mission to understand the change in groundwater on land masses, the exchanges between ice sheets or glaciers in the ocean, and solid earth mass changes also from earthquakes. So this was first proposed back in the 1950s, that you could put a pair of satellites in orbit and measure the change, the distance between them, measured as microwave interferometry or laser interferometry, and we're using both today. So this gives us the ability to measure the groundwater. And here's an example of, this is California, there we go. So you can see the chart on the map on the right. You're seeing the change in the groundwater over a period of time. The other thing you can see about it is it's fairly coarse. The resolution is about 300 kilometers. So over the long term, there is a need for better precision. And that's why we have started investing in a quantum gravity gradiometer, which we hope will address some of those needs. So the QGG has the potential to create much more precise measurements of the gravitational field than we're currently getting with GRACE. This technique is probably, in terms of quantum sensing, it's probably the most mature. And we think this technology demonstration will give us a pathfinder approach for new types of quantum sensing missions in the future. So we're looking forward to developing this technology demonstration. So um, the approach here is to use ultra cold atoms that are generated. These are Bose-Einstein condensates that are generated from the ISS. There's two critical subsystems here, the atomic physics package and then a laser optical system. So the purpose here is to interrogate the atom as it's dropped and then measure the difference, the difference in the motion of the atom after the non-Newtonian effects are removed. And that gives us the measurement of the gravity to a 10 times more sensitivity than we have today. So the ability to do this will help answer new science questions, global sea level to higher precision, ocean heat, ice sheet mass change, glacial isostatic adjustment. This is measuring after the glaciers slide off the land, groundwater recharge, water availability. So it's really a game changer in terms of our science. So that will be our first investment in quantum sensing. I do want to make a couple of remarks on the modeling, if there's time. I didn't have charts on the modeling. We have a big investment in modeling and simulation in the Earth Science Division. We model the Earth as a complete system. We model the atmosphere. We model the chemistry, the oceans. We also have models at fine resolution, at mesoscale. We have models of wildfires that model the spread of fires after they occur. We have seen the new investments in artificial intelligence and machine learning have had a profound effect on these models. The physics-based models of the atmosphere, which effectively solve the primitive equations of the atmosphere, over time, they roughly are 5 days per day in terms of prediction. So it takes a day of computer time to produce 5 days of simulation. What we've seen in the last couple of years is a huge disruption in our ability to perform modeling. Machine learning has been performed on reanalysis data sets that have been developed over a period of time. So we have a 40-year reanalysis of the atmosphere going back to about 1980. Google, working with the European Center and also with NOAA, have been able to produce forecasts based on machine learning from those databases that are 3 to 4 orders of magnitude faster in terms of computer time than what we're seeing by solving the physics-based models. So they're effectively looking at patterns in those databases and reproducing them for predictability. To say it's a disruption might also be a mistake, because usually with disruptive technologies, it's faster or it's better in some aspect, but the result is not as good. If you think back to the early digital cameras, which were blurry images at first, but then over time they overtook the film cameras. What we're seeing with these models, with these machine learning-based models, they're already getting results as good as the physics-based approach. So this could open up a whole new area for science research with these models, because now they're so much more useful and they require so much less time in terms of computation. So we'll be looking at that. We have programs that are investing in those areas as well. And we think that for wildfire modeling, it'll also be very useful going forward. So that's a little bit about technology investment. I'll turn it over to Mike to talk about how we're investing in wildfires.
All right. Good evening, everyone. Thank you, Mike. Thank you, Larry. It's really a pleasure to be here. I'm excited to be here. As Larry mentioned in my introduction, one of my first jobs after I finished my undergraduate degree was working for a tribal organization in Wisconsin where I got to learn about prescribed fire and actually got to be a wildland firefighter. I was an academic for nearly 10 years after grad school and did a lot of research on trying to figure out how to use Earth observation data to support a wide variety of resource management questions, including wildfire, and have been at NASA since 2018 as a program manager and got into the wildfire business again about 3 years ago. So it's been a really fun ride and really fun to re-engage with the wildland firefighting community to bring technology to bear on a very important problem. So Mike already showed you our fleet chart. This is another version of that, except it's animated, showing you all the different Earth observation satellites that we have in orbit, at least as of December 6th, 2024. I think we have somewhere around 25 or 30 missions in orbit, each designed to measure a different component of the Earth system, and they work together to give us a holistic view of our planet Earth and how it works. And a lot of these satellites that you see here have direct application in wildland fire management, which I'll talk about today. And so when we talk about wildland fire management, we're not only interested in the active fire, but we're interested in understanding the factors in the pre-fire environment that lead to increased fire risk and how we can potentially mitigate that risk, but then also things like recovery in the post-fire environment as well. This is a snapshot of some of the data sets collected with our Earth observation satellites, looking at things like sea surface currents, our Blue Marble product looking at the biosphere, so photosynthetically active vegetation both in the water and on the land surface, soil moisture, weather patterns from the iMerge data set across the globe, and of course clouds and aerosols and other aspects of the Earth systems. And you can imagine, as I mentioned before, when we think about fire across the life cycle, all these data sets have relevance to not only understanding how fire, the role it plays in the Earth system, but how we can also better management across the Earth. We've been measuring active fire globally since the early 2000s. Mike mentioned the Terra and Aqua missions, which have a sensor on board called MODIS. I don't know if this played or not. Oh, let me go back. That should play. Go back one slide. Not sure why it's not playing. That is an animated slide if there's any way you could click it. Yep, thank you. So this is a year in the global fire life cycle as measured by MODIS. So this is FRP, fire radiative power. It's basically showing you the energy output from fire within individual pixels across the Earth's surface, and you can see that our planet burns a lot. A lot of these fires are intentionally set for management reasons, especially if you're seeing right now in the grasslands of Africa, a lot of fires that are intentionally set for managing those grasslands. We also set a lot of agricultural fires intentionally and prescribed fires as well. So we've been measuring with MODIS and now VIIRS, which is a sensor operated by NOAA, fire in the Earth system for over 25 years with these types of data sets, and we've learned a lot. And I'll talk a little bit about that later in the presentation tonight. We can also measure air quality from our satellites. This is an animation of carbon monoxide from the fires that happened in Canada, I believe 2 summers ago. If you were in the DC area or the eastern seaboard during that time, you remember how bad the smoke was. So this is actually a modeled output from our Global Ecosystem Office up at NASA Goddard, where they're taking some Earth observation data sets and putting it into a model to simulate carbon monoxide production from the Canadian wildfires, which is, of course, carbon monoxide is very harmful to human health. And so data like these can be used by our partners in places like the EPA to improve air quality forecast models. And that's something that we're doing currently with those partners in the wildland fire space right now. This is another look at the MODIS and VIIRS data sets. And so what we're looking at here is a fire in California that happened back in 2021. The orange triangles are individual hotspots from the MODIS and VIIRS data. And what some folks at Goddard, NASA Goddard Research Center up in Greenbelt, Maryland did is they applied some AI to this to figure out where the fire perimeter was on a 12-hour time basis. And so a data set like this is very useful to our operational partners in the wildland fire management agencies for a variety of reasons. In the operational response to fires, data sets like this can help them understand where the fire is spreading so they can pre-position resources and or get resources out of the way in high fire danger situations. But then we can also look at factors after the fact that help, or not that helped, but that led to really large fire spread events and use that to make better management decisions going forward. We have been operating in conjunction with the USGS, a sensor called Landsat, to measure the Earth's land and ocean surface properties. And it has been used widely since the mid-1980s to look at a variety of aspects of wildland fire. What we're looking at here on the left is an image from the Smokehouse Creek fire, which burned in the Texas Panhandle back in February, about a year ago of 2024. That particular fire burned from a couple of weeks, but there was a few days of really fast fire spread. It burned over 1 million acres. It killed 2 people. It killed nearly 7,000 cattle and burned over 100 homes. So it had a lot of negative impacts, of course, to the local economy. But from this Landsat time series record, which goes back to the 1980s, we can see that we've had a marked increase in the amount of area burned within the United States over that several decade period. And so certainly we are seeing that fires are becoming larger. Not only are they becoming more frequent and more common, but they're becoming larger, and they also occur close together, both in time and in space. So this is a look at co-occurrence of large fires between 1984 and 1989 versus large fires between 2005 and 2018. And so you're seeing a big drastic increase in the number of large fires. And we certainly expect that this trend will continue with warming atmospheres. This is a model or a map showing you something called vapor pressure deficit, which is essentially the dryness of the atmosphere. And as the atmosphere becomes warmer and drier, it is sucking more moisture out of the soil surface and the vegetation. And so these ecosystems become more flammable when a fire does occur, because of course there's no moisture to sustain the vegetation, and it burns. They burn a lot hotter in those drier conditions. And of course, we expect this trend to continue going forward. We also are seeing with our MODIS data increase in fire intensity across the globe. So this was a paper published this year in, I think, Nature or Science, where they took the MODIS time series data, or a time series of the MODIS fire radiative power data, and looked at how intense fires were burning across that time record. And you're seeing indeed an increasing trend in the amount of energy output by fires across the globe. On the left-hand side of this slide here, we have a satellite image of a fire in the LA area this past summer called the Line Fire. There was, I think, 3 different fires going on at this particular time, and this is a pyrocumulonimbus cloud from the Line Fire. Those pyro-CBs are very dangerous. These are the fires that create their own weather patterns, and they're extremely dangerous for the the firefighting community. I'm going to grab a little water here. And we recently funded a field campaign specifically looking at how to better predict pyro-CBs and how they behave, and one effort into better understand the role that they play, not only in their system, but how we can better protect the firefighting community from events like this through better predictions. So we are also seeing an increase in the number of extreme events. So of course, this just happened in LA, as you know, a couple of weeks ago. But here's a look at the 2020 Labor Day fires that happened in Washington and Oregon. This is a really interesting story from a sort of a global weather pattern analysis. So what had happened was you had several small fires burning in California, Oregon, and Washington. And then you had a series of 3 typhoons across the Pacific, and they caused the jet stream to drop really far south, and you had these intense winds pick up, and you saw extreme fire spread across a 2-day period in this particular location. In Oregon, the Labor Day's fires burned for 2 days. You had 60-mile-an-hour plus wind gusts, 100-mile-an-hour wind gusts in some areas, 850,000 acres burned, 4,000 homes destroyed, and 11 lives lost. And on the right-hand side, you're seeing some wind modeling that we've done with some of our data sets to better understand how the winds moved through these landscapes and led to those extreme fire behavior conditions that we saw. Another paper that just came out a few weeks ago, actually, using the MODIS data to look at what we're calling now fast fires. So these are the extreme events like we just saw in LA. What this paper basically observed was that these really fast fires, these ones that have wind events with fire in them, accounted for 78% of the structures destroyed and over 61% of the suppression costs. So the story here is that a small number of fires are the fires that are actually causing the largest problems in terms of impacts to the economy and human lives. And again, we expect with our changing Earth system that we will see more fires like this going forward. This is a video from LA showing you embercast, just to show you how intense these situations are when you have extreme winds that have an ignition in them. So these are embers cast from a palm tree, or palm trees, which are not native. And I saw an AI image or AI analysis of this particular video, which is about 5 seconds long, and there was over 7,000 embers generated from that fire. And so a couple of points here is that when you have fires like this, where you have extreme wind, they become really hard to suppress for the firefighting agencies. They're very dangerous. And so basically the only thing the fire crews can do is get out of the way, evacuate people, and then hope the winds die down so they can stand a chance to get ahead of it. This is an image of the Paradise fire in California back in 2018. Again, not great statistics here. This burned on November 8th of 2018, 150,000 acres. 90% of the town was lost in terms of the structures and 83 fatalities. One of the interesting things that you will see in this image is that the vegetation is largely intact. And so there is a big difference in fire behavior when you get it into a community in these high wind events, which are called community conflagrations or conflagrations, as opposed to a wildland fire out in areas that are out in the surrounding wildlands. In this situation, the houses themselves become the fuel, and it's not the vegetation that becomes the fuel. So what you're having is, if you remember the ember cast from the previous image, you have all sorts of embers that are staying close to the ground, and they start to accumulate at the base of the houses and eventually build up enough heat to ignite those houses, and that just propagates through the community. The trees themselves, the vegetation itself is largely left intact. And this is a very common pattern that we're seeing in these urban fire events. And here's another look. Again, the vegetation largely untouched, and so it's the houses that become the fuel. It turns out there's a lot that a homeowner can do to start protecting their houses. Here's an image from a fire in California where you have a house that has taken a lot of actions to protect themselves from fire. They've installed the metal roof. They've moved vegetation around from their house. And in the end, this particular house survived. And if you look at this particular image, you can see that there's actually a firefighter sitting right there that decided that house was salvageable, and they were able to, through their triage approach, decide to invest their time and put their life on the line for a house that was actually savable versus one that may not have taken those preventative actions. And really, when we think about fire suppression, there's a big paradox. So a lot of the ecosystems, especially in the Western United States and other parts of the world that are similar to that, have evolved with fire. And so on the left-hand side here, we have a ponderosa pine forest, where we have a surface fire burning. Again, these ecosystems can tolerate fire as long as the forest structure and the vegetation structure are open like that, and there's not a high density of vegetation. You can see that these firefighters here are not too concerned about that particular fire. They're walking away from it. They may have even intentionally set this fire for ecosystem restoration purposes. Because of fire suppression in the United States and other parts of the world where we've been actively putting out fires for over 100 years, you get an accumulation of vegetation in these ecosystems. This is essentially a system that has a lot of energy to release, and so when it does light on fire, they become way more intense than they would be in a sort of a natural situation. So the paradox is the more fire we suppress, the larger and more intense the fires get. And I want to reiterate something about, or I want to also mention that not all fires are bad. So this is a fire that I hiked through in Oregon near Mount Hood this past summer. This was the Dollar Lake fire that burned in 2011. Again, you can see just based on this image that it was a really intense fire. Almost all the overstory trees were killed. But now, 12 years later, we're seeing a very diverse ecosystem, very healthy trees regenerating. And so when we think about fire and fire impacts on a lifetime of a human, on a human time scale, they seem very devastating to ecosystems. But as a matter of fact, ecosystems largely respond very positively at a longer time scale. And so this is a time-lapse image of some of the vegetation regrowth in an area near this particular fire. And we also see that in certain areas, like again, this is also in near there, this is near Hood River, Oregon, a fire that burned around the same time. Again, 12 years later, we have wildlife coming in almost immediately right after the fire. And so these ecosystems respond quite positively to fire in the long run, and do actually, in most situations, recover quite nicely. And so right now, what we're doing in the United States is starting to look at how to better manage and mitigate wildland fires in different situations. And so there's this idea of building communities that are more resistant and more resilient to fire. So intervening before a fire becomes a problem. So removing vegetation around houses and in the wildland areas near communities through either mechanical treatments or prescribed fires. Enhancing safety of evacuation routes, for example, better management of the power grid. So many of the wildland fires that I mentioned today were started by power lines and high winds. So knowing when those high winds are coming and when we might need to de-electrify the power grid is another thing that we can do in the preventative measure. And then we can also restore ecosystems to a more natural state. So we can either do that through reduction in the fuels in the vegetation and or reintroducing prescribed fire into the ecosystems. And so on this particular image here, you're seeing a image after the Bootleg fire in Oregon, where it was a natural experiment. Just the Nature Conservancy was doing a test on impacts of forest thinning, impacts of thinning plus prescribed fire, and then no treatment at all, and then a wildfire happened to go through, and you can see drastic differences in the ecosystem impacts of that particular fire. And then, of course, in other places, and I'll talk about this particular site in a second, this is actually a very large intentionally set prescribed fire in Utah that is meant to restore ecosystems to their natural state and also reduce fuels and fire risk for local communities. So real briefly on the wildland fire program that I manage, so we're, like Mike mentioned, we do a lot with technology development. So we're investing in foundational technology to better understand and measure wildland fire. We invest in the research and applications that leverage Earth observation data to help do that as well. And really try to improve the end-to-end management of wildland fire to ultimately reduce the impact that fires have on communities and the economy. We work closely with the fire management agencies in the United States and globally, researchers at academic institutions. We fund a lot of private companies directly as well. And again, we're trying to do an end-to-end investment in the technology and application, or the development and application of the technology. And so through Mike Seablom's ESTO program, we've invested in a lot of foundational technology in fire. We do research and analysis with that data. We work with our end users to co-develop applications, and then ultimately we want to transition those technologies into operations within our fire management agencies in the United States. I mentioned MODIS earlier, which has really been a foundational technology not only for fire science in the Earth system, but also has been directly used to support fire management in the United States and across the globe. We deliver MODIS data and now VIIRS data actively through our FIRMS system. And it's used by the US fire management agencies as well as countries across the globe. In some parts of the world, these are the only active fire data sets that are available for fire management. This is a picture I took at the National Interagency Fire Center in Boise, Idaho. So during an active fire season, they have FIRMS up on the screen. They use it in their morning briefing to understand where the fires are, how much they grew overnight, and how to then they make decisions on resource allocation, where they're going to send more engines and more fire crews to manage those fires. We're continuing to invest in different types of technology to measure fire, again, across the fire life cycle. So a couple of examples of things that are currently in orbit or will be in the orbit in the future. One is JEDI, which is our Global Ecosystems Dynamics Investigation. It's a LiDAR, a vegetation LiDAR in the International Space Station, specifically designed to measure the height and density of forests. And we're investing in projects right now. This is an image of sorry, I lost here. Image of JEDI data across the Pacific Northwest, showing you forest height. We've got projects invested in my program looking at how we might use the JEDI data to better understand the distribution of fuels across the landscape to, of course, for mitigation purposes. We recently launched TEMPO, which is a air quality mission looking at tropospheric composition. And TEMPO was recently used in the LA fires to look at the air quality impacts of the LA fires. We have EcoStress, which is a thermal sensor on the International Space Station. Again, this is an EcoStress image here from the recent LA fires, showing you the temperature of fire across that area when that image was required. Very soon we'll launch NISAR, which is a synthetic aperture radar in conjunction with it's a joint venture between NASA and the Indian Space Agency. And there's a whole variety of applications in wildland fire that we can use SAR data for. One is looking at vegetation structure. Another is soil moisture and fuel moisture. So really getting at high resolution and increased temporal resolution measurements of fuel moisture, which can improve assessments of fire risk. And then further out into the future, we'll be looking at SBG, the Surface Biology Geology mission, and also Landsat Next with the USGS, which are both hyperspectral missions, and there's a whole wide variety of applications we can use those data for to support wildland fire management. One of the projects within my portfolio is called NASA FireSense, and this is a project that's really largely focused on transitioning technologies into operations. And so we are very good as scientists and technologists at developing new tools, but sometimes it's really hard to get our end user organizations to adopt those tools for a variety of different reasons. There's lots of barriers to integration, especially when you're dealing with something like wildland fire. And so FireSense has been specifically designed with our stakeholders in mind from day one. They've helped us design the program. We've had many workshops with them to help with project design, and now they are working together with our scientists and technologists to identify problems and co-develop solutions with the idea that they can eventually transition these into operations much easier than has happened in the past. These are some of the things that we're looking at in FireSense. Again, it's across the fire life cycle, so making improvements in understanding the pre-fire environment, the active fire environment, the post-fire environment, and then also air quality. One of the unique things that we do at NASA and specifically in the FireSense program is something called field campaigns, where we take our technologies into the field on aircraft and sometimes on satellites as well, and we really intensively measure different ecosystems or different phenomena across the Earth's surface. We're doing this with fire, where we're taking the new technologies that we're investing in and bringing them out into the field in active fire situations and working with our partner organizations to demonstrate how that technology works. And again, with the idea of hoping that that leads to better transition. If they understand how the technology works and how it works within their operational framework, then they're more likely to adapt going forward. I'll give you a couple examples of some of what we've done over the last few years through some of these airborne technology demonstrations. We did our first demo back in 2023 across several sites in the western United States. And again, we were measuring things like fuel moisture and soil moisture, active fire dynamics, and post-fire impacts. We also conducted one up in Missoula, Montana this fall, which I'll talk about really briefly. And then we're about to do 2 field campaigns this spring down in the southeastern United States, one in conjunction with Alabama State Forestry Commission, which burns a lot for timberland management, and then Merritt Island Fish and Wildlife Refuge, which is part of Kennedy Space Center. And they burn for a variety of reasons, for ecosystem management goals, but then also to protect the Space Center and local communities from catastrophic wildland fire. This is a video from our Utah field campaign where we took a bunch of our aircraft into the field and worked directly with the Forest Service on the Fish Lake National Forest in Utah. The Fish Lake National Forest in Utah sets very large canopy fires to restore aspen ecosystems, which you'll see here in a second. Aspen ecosystems need fire to regenerate. They are very important ecosystems for wildlife, including elk and grouse. What has happened during fire suppression, the era of fire suppression, is the conifers have encroached into the aspen. The aspen are dying off, and the ecosystem health is degraded. And so the Fish Lake National Forest has a very comprehensive plan to light these large 5,000-acre fire in this case to restore ecosystems, and they intentionally light canopy fires. So these are very intense fires. We bring our aircraft. We have folks in the field doing ground measurements. And again, we're doing this to demonstrate how our technology might work in a wildland fire situation in a controlled and safe environment. That's one example. This is a campaign, or just a little tech demo we did in Missoula, Montana this past fall. The U.S. Forest Service and the National Weather Service were very interested in using new technology to better improve fire weather forecasts. Typically, you would take these kind of atmospheric sounding measurements with a weather balloon, but you can't do that on an active fire incident because the weather balloons, of course, will interfere with airspace operations. And so we had an idea of putting an atmospheric sounding instrument on a drone that you could just fly vertically and in a controlled environment and keep it out of the way of the airspace operations. And we were successfully able to demonstrate that worked well, and the data were used in real time to improve fire weather forecasts. So ultimately, you could do this on a wildland fire event and improve fire weather forecasts to protect firefighter safety, but then also better manage that particular fire by getting a really detailed local forecast. Finally, another demonstration that we did this past summer with the U.S. Forest Service, and we'll do again a version 2 this coming summer, is called Strato. This was a collaboration across a few mission directorates within NASA, including the Earth Science Division and our Space Technology Mission Directorate, along with the U.S. Forest Service. This solves a couple of problems in wildland fire management and wildland firefighting. When the operational agencies are out fighting fire, oftentimes they're doing so in areas that don't have communications. Cell towers are absent, and so there's a big need to try to figure out how to improve communications in these environments. And so what we did this past summer was we put one balloon in the air with an LTE package on it. So basically it worked as a cell tower in the sky. And we were able to demonstrate how that could be used to improve the communications between the fire crews out in the field and the incident command post, which is often many, many miles away from the firefighters. The other thing that we were able to do in this situation was put an IR camera, an imager on that balloon, and we were able to take images of the fire and send them to the incident management command post in near real time, within a minute or two of acquisition. And so I was actually at the fire camp where the data were coming in, and the incident commanders were shocked and impressed with how game-changing that particular technology could be. And so we did that with one balloon this past summer. We just invested more money with the U.S. Forest Service to do this again with 3 different balloons, and we're going to test a few different sensors and expand the coverage. So that's the end of my talk. Thank you for your attention.
So we're going to start with the red microphone.
I'm Julia, and I'm a guest. So, will there be more like high wind or fire tornadoes in the future?
What was the question? Could you repeat?
Will there be more fire tornadoes or high wind fires in the future?
Yeah, we expect to see what we just saw in LA to happen again, and potentially more frequently. Yes.
The blue microphone. Paul.
Yeah, Joe Wilson, member of the Society. 2 questions. One with the fires. From your spatial observation, have you been able to feed it into, say, modeling of how fires move? Because I think in what happened in Palisades, it looked like there was a heat wave drawing the fire plus the wind. And the second question is about materials, and this is a crazy idea that just crossed my mind. Thinking about something to protect homes, transferring some of the technology we use to make material that allows spacecraft to re-enter into the Earth, sort of like what's on the space shuttle, those bricks that can take high.
Yep.
Do you think that's possible?
So answering your first question, regarding whether or not our data are used to improve fire forecasting models, the answer is yes. The problem with a lot of our space-based observations, like the ones that I showed you from Modus and Veers, we're getting 2 to 4 looks at a fire a day, which isn't not really sufficient for improving fire behavior models because fires spread really quickly compared to that. We have been able to use, in some cases, some aircraft observations to do that as well. And then there are other assets on the classified side that get more frequent observations that are being used to improve fire forecasting models or fire spread models. Another thing is the commercial industry is very interested in developing small satellite constellations for fire management, and some of them will get 8 to 12 minute repeat. Those types of data, once they come online, can certainly be used to improve fire behavior models. Regarding building materials, I mean, I think your idea is an interesting one. There are agencies like NIST, for example, and they have a lab up in Gaithersburg, Maryland, that do a lot of material science related to improving or reducing the flammability of homes. They actually have a facility there where they can burn entire buildings and take high resolution images and understand how fire spreads through homes with different materials. So yeah, I think it's a good idea.
Take a question from the YouTube chat. Let's turn the microphone on for that.
Yep. Our first question online comes from Eric in Sweden, who is not a member. Is it time to stop building houses out of materials like wood, shingles, plastic, and foam in fire-prone areas?
Yeah, very much related to the last question, the last answer. Yeah, I think there's a lot we can do in terms of using different building materials, but then also, putting on metal roofs, removing vegetation from around your house, removing wood fences, things that can propagate your house or fire into your house. One of the things we see very commonly is those embers will get into the house eaves and start the roof on fire. And so something as simple as putting a screen over your eaves to prevent those embers from going in can make a big difference. So yeah, there's lots of options that people can take in their own homes to reduce the risk of their house burning down.
Another question from YouTube.
Oh, yeah. Michael Haken from Silver Spring, Maryland, who is a member, asks, what is the zero reference for the ocean surface topography anomaly data, and over what temporal interval are the measurements averaged?
I don't have that answer. That's a good question. I don't know what the zero reference for SWAT is.
I don't either.
Yeah. I'll have to circle back on that.
Red microphone. Pause. Tell us your name if you're a member.
Hi, my name is Hayden. I'm a guest. On the sort of fire suppression paradox you were talking about, when a fire does rip through a certain area, does that bring the overgrowth in the area back to zero, or are you still dealing with that like baseline overgrowth, just slowly reducing with each fire that goes to the area?
It depends on the intensity of the fire, but certainly in some of the photo I showed where that you had that really dense situation. If the fire gets in there and the wind is sufficient, you would expect total consumption of the vegetation. And again, you would expect at some time interval that forest would regenerate either naturally or, the U.S. Forest Service, for example, will do a lot of replanting after fire to help restore ecosystems.
Got to go to the blue microphone.
Runoff, remember, would more frequent satellite overflights provide exponentially better fire predictive data?
For fire prediction?
Or
or-
at least modeling current fires?
Yes. So if we had more frequent observations, that would be game changing in terms of being able to develop models that are more accurate in terms of fire spread. A lot of the models of fire spread that our land management agencies use, our fire management agencies were developed in the 1970s, and so they're quite old, and they could really benefit from better observation to improve how they work.
So the fire spread model you're talking about is the Rothermel.
The Rothermel models.
Rothermel model, so that's a physics-based model. So if we had enough observations, we could perhaps use machine learning instead. That requires a lot more information gathering, and in these field campaigns, we're a long way from that.
But that's one of the things we're doing, especially at Merritt Island Fish and Wildlife Refuge this spring, is we have a bunch of researchers coming in the field. We have lots of cameras and other things trained on the fire. We have satellites that'll be trained on the fire. And one of the goals is to use that data to improve fire spread and smoke forecast models.
Let's go to the blue microphone. It's on. It is on.
Yes, my name is Frederica Derima. I'm a member. Thank you for your extensive presentation, talking to us about the instrumentation and then kind of the wildfire incidents. I was very much surprised to see when you showed the worldwide map that there were a lot of fires in the Brazilian, which I was going to ask, are these because there is a lot of burning of the forest intentionally there?
Yes.
But I was even more surprised to see the swath of fires in Africa. So what causes that? And I was not aware of that, and we
Yep.
had never heard of that in the sense that there are so many fires in Africa.
So, sorry.
And then my other question is, given this worldwide, what is, and the European ESA, for example, the European Space Agency, I saw in one of the airplanes had an ESA there, maybe it
yep.
was ESA, yes. So what is the collaboration across the globe in terms both of instrumentation and models? And I have many more questions, but maybe
So
another.
let me remember. So the first one was about Brazil. And yes, what you're seeing in Brazil is largely fires associated with land conversion from tropical forest into agriculture. And so it's the slash and burn situation. But then some of those will also happen naturally once those ecosystems get degraded. In Africa, the ones that you're seeing farther south in Africa are a lot of intentionally set grassland fires, again, for land management purposes in the savannas. Again, that promotes regeneration of the grass, which is good forage for livestock and wildlife. And so those are intentionally set fires as well. That's the other thing I'll point out is something like 82%, maybe it's 78% of the fires that we see in the world are intentionally set, or I should say non-natural ignitions. And then your last question was, oh yeah. So we do collaborate internationally on the fire topic as well. So I mentioned MODIS and VIIRS, for example. MODIS was our instrument that's been in orbit for about 25 years now. It's going to get deorbited soon. It's was only designed to work for 3 years, and it's been doing a lot better than that. And it's become very important for understanding fire in the Earth system and observing fire globally. But one thing we've done is the Europeans have a satellite called Sentinel-3. And so we're trying to figure out how to transport our algorithms to Sentinel-3 so we don't lose that data record going forward. That's one thing that we do with the Europeans on fire. And I mentioned NISAR with the Indian Space Agency. That'll have a lot of fire applications. And then the Canadians are currently building wildfire satellite constellation that we're interacting with them on that. And then there's the Australians are also interested in doing that. There's some private ventures globally doing that as well.
Yeah, there's quite a bit of growth in the commercial sector.
Yep.
Philanthropies are providing funding.
What are the industries? That was my corollary question that are involved in that.
Stand up and hold the mic to your mouth.
What are the industries, some of the industries that, if you can give us some examples?
For the space-based detection of fire, there's a few companies looking into it right now. The furthest along is as Mike mentioned, it's a venture that has been funded through philanthropic organizations. The Gordon and Betty Moore Foundation have provided funding. Environmental Defense Fund, Google.org have provided money to a company called Muon Space in Mountain View, California. They're going to launch their first satellite in a month or two. And it'll actually be active over our field campaign, so they'll be able to test their instrument over our field campaign. There's another company in Germany called Oratech. What are some of the other companies? Honeywell's got some interest. Planet is another one that has some interest in this space.
Yeah, Planet is looking at
Frederica.
going into the thermal infrared.
Let's let somebody else ask a question now. Let's go to the red microphone, please.
My name is Mike Hilton. I'm a member. My question has to do with the detection of an early fire as it first gets started. It seems to me that if you have the right technology in place, you can rush out to have a first responder firefighter and system get out there before a fire takes effect and gets too big to control. Do you know if NASA has studied any kind of a system of satellite IR detectors where they have also a communication system that can communicate directly to a fire outlet right near a detected fire that first starts, not after it started, but after it gets going, but after it first starts.
So a couple of things regarding that. So as I mentioned, a lot of our satellites, like MODIS and VIIRS, don't provide high frequency enough measurements currently to be able to do that. There are other technologies in place that can do that. There are some classified assets that are used in that regard. In places like California and Colorado, there's actually cameras on towers that are used like how a fire tower used to be used, that can automatically detect fires, and they do catch a lot of fires that way. But oftentimes, like what you saw in LA, for example, there was the winds were so intense that once the fire started, there was just nothing you could do. There was a video online. I couldn't show it tonight because of copyright reasons, but you could go online and look at the start of the Eaton fire, which is the one that went through Pasadena. It's a matter of 5 minutes from when that fire is first detected to sort of the catastrophe unfolding. So in these high wind events, even if you detect the fire instantly, there is not much you can do.
So a comment and get your opinion. So waiting for the fire to be detected might be like a goal line stand. I mean, we're also looking at the fuel loads. We're looking at the pre-fire conditions, which will make observing those areas more intensely perhaps a better approach.
If you talk to the firefighters, especially especially in the United States, they will tell you, a lot of them will tell you detection isn't the problem. You can make a lot more gains by better protecting your communities before a fire even starts.
Thank you.
Yep.
Okay, blue microphone, wherever that is. There we go.
Hi, my name is Linda Voss. I'm a member. I wanted to thank you very much for this really fascinating presentation. It's a fascinating topic. And I wanted to kind of focus on the philosophy of management of fires, like preventing fires going into the future. And I'm going to pick up on some threads. I'm not sure if I got them correctly. It sounded like you maybe started in a tribal community working on prescribed fires. So there's a tribal, perhaps, philosophy.
Yes.
You've been on the fire line, so you've been a firefighter, and there's what you do when you're in that very intense situation. Having NASA be involved in this, I find fascinating. I noticed there were a number of joint ventures with the U.S. Forest Service, which would be the service that you would think would have the major responsibility in this area. And then there's, of course, all the technologies involved and things you could talk about. I had a cabin in the Shenandoah, which was in part of the flames there. So I know how complex it is to allow fire to burn. So could you give us a kind of perspective on philosophies of fire management and the kinds of partners involved and maybe the major players or who has the major responsibility for determining in any given community what you might do in terms of fire management, prevention, forestry management, and fire prevention?
I can try to address that. So it's it's a very complex space because you have multiple jurisdictional authorities when it comes to wildland fire. So, for example, at the community level, you have your local fire department is the primary point of contact. But then, when a fire gets started and gets out of control, then maybe if you're in California, Cal Fire takes over. Or if you're near Forest Service lands, the Forest Service might take over. And then you have the BLM agents or the Department of Interior agencies like the BLM or the National Park Service. It can get really complicated in terms of who has the jurisdiction over that particular fire. If you're thinking about community level stuff, the local fire department is the place to go in terms of figuring out how to protect your home and your property in the pre-fire environment. But then there's also a lot of state and national programs to help do that as well. I don't know if that's helpful. But, yeah.
Did that answer your question? Kinda.
To the future, like managing forests prescribe fires, those
Yep.
sorts of things, and who would, what the philosophies are and who might be the philosophy that dominates.
Yeah, I mean, so again, it depends on the agency that's responsible for managing that particular piece of ground. But there is a recognition in the fire management community that we need to return ecosystems that have evolved with fire to a landscape that accepts fire again and has fire as a beneficial process in those ecosystems. And so, we do in this country, we do a lot of prescribed fires. They can be hard to implement sometimes because of perceptions that communities have about fire risk. Also, because of smoke impacts, prescribed fires put up smoke, and those smokes will impact communities. And so, there is a big component of this in terms of sort of shifting some of our communications around that and getting people to buy into the fact that we need prescribed fire, and you need to have a little bit of smoke exposure in controlled environments rather than these big wildfires that are devastating and have really major smoke impacts.
Red microphone.
Member. Understanding that a lot of the worst Western wildfires originate with power lines, investor-owned utilities, and so on. Unfortunately, there's also sometimes, as we saw in LA, I guess, a component of criminal arson, and then you've got people making illegal incursions into airspace with drones and so on. Are there any law enforcement applications to this kind of remote sensing? Like if we were able to, find the origin or earlier of when the fire started, would that help in enforcing the laws around these types of things?
Absolutely. And so there are organizations that will do, especially in the after a fire, they'll do investigations for those very purposes, and they will use remote sensing data sets, some provided by NASA, to help aid those investigations. In the situation of the drone incursion, that's another problem that we're working on at NASA. Our Aeronautics Research Mission Directorate does a lot with air traffic and air traffic safety, and they actually have systems that could prevent that kind of thing from happening in the future, and also allowing multiple aircraft to operate simultaneously, fixed wing piloted aircraft and drones in the same airspace safely. And so those are other things that our agency is investing in.
I actually got to interject a couple of questions, and then we'll go to the blue microphone. So I'm Larry Milstein. I'm a member, and probably many of you know. So the first question is, I went to an exhibit at the Building Museum, and it was about building with wood, tall buildings, 20, 30-story buildings. And as part of talking about that with another member who is a structural engineer, he told me that steel actually is more flammable than wood. So as to the question that was asked earlier, as to maybe it's time we stop building with wood, I think, would the question be better framed that we should build more smartly with wood, or is that completely wrong, that wood is really more flammable or easily inflamed than wood? So I wonder if you could shed some light on that.
Yeah, I mean, I'm not a material scientist, so I don't know if I can really answer that question very accurately. But we do see in these fires, like the ones that just happened in LA, that wood buildings do survive. So there are other factors beyond just the material that's used that contribute. So again, something as simple as a metal roof or putting a screen over your eaves could make the difference of your house surviving or not surviving, regardless of the material that's used to construct it.
My other question is an existential question of a sort that I ask a lot of people, because everybody's reading about AI these days, and more we're hearing from people that they are using large language models and AI to make predictions. And you were telling us that it's a game changer. It's disruptive. It's giving better answers for orders of magnitude less computational time than what is based on physics. And the same things, just recently read, for lack of a better word, an AI that was designed to design electronic circuits. It's able to design an integrated circuit that did its job better than anything that was made by very sophisticated circuit designers using very sophisticated circuit design software. But people have no idea how it works. they look at the circuit and they don't really understand why it does what it does. So I guess my existential question is, do we care about understanding what it is, how the artificial intelligence of the program, or whatever we want to call it, how it knows what it knows in order to predict better than other systems what it predicts? Or do we not care?
So this is a great question, and it came up at the American Meteorological Society conference back in January. So again, the way the operational weather prediction models using machine learning, the way they work, they take a 40-year reanalysis of the weather and they predict based on what's in the database. So it's nothing but nonlinear regression. That's all it is. What I find fascinating about it, and I spent years using linear algebra to perform analysis of the data, and we estimated the covariances, the structure functions of how the various types of data interacted with each other. And what they're able to do now is they know the true relationships. They actually, with the machine learning, we know the actual values. And what we were doing back in the day were tuning knobs, really. So your question is, you perhaps get a more exact representation of all of those features, and it's all buried in the machine learning. It might be possible to retrieve those relationships. I don't know how to do that, but I think there are people who can.
There are people working on making their machine learning algorithms so you can
But the physics,
look at how it does what it does.
Based approach won't go away. I think it's not a replacement for that.
I think it's an interesting question. Blue microphone.
Kristen Ferry, and I am a member, and I'm going to dedicate this question to Carl Merrill, another member who couldn't be with us, because of a conversation that got me thinking about this. In these large models that you're doing with so many different types of data, and you're seeing climate impacts over time, as for instance, you showed the polar ice. Do you include in your inputs the solar cycles, the solar flares and storms? And if so, does that appear to be a significant influence in in the climate variability that we see? Not necessarily the long-term trends, but the high variance that we're seeing?
They're not included in the global climate models because I think there's a belief that if you do a scale analysis, it's not a major factor, but it's something that I think there are scientists out there looking at that for sure. Now, the other thing you pointed out, the climate impact for a climate model, we don't have a long-term trend where we can use a machine learning approach. That still has to be the physics-based, or at least physics-assisted.
We're going to take just a couple more questions. We're going to go to the, red microphone.
Jason Eckberg, member. Thank you again for the wonderful presentation. I'm going to keep pulling on this thread. Larry sort of took the first question that I had, and then she took the next one. But it kind of comes back to what you were just alluding to. As you're seeing the observations for the last 4 decades that you've been using to make to be able to make the predictions in the climate and the kind of processing power that's required for that. You alluded to 1 day of processing power for 5 days worth of predictions that are going to, with all of the inputs that are coming in, to be able to see what is going to happen. With the changing assumptions like surface temperatures rising, like you had shown in one of the charts that you have, are we starting to see edge cases happening more often? And what is the veracity of those edge cases, especially as the intensity of storms and the intensity of what appears to be fires increasing in frequency showing up? And how are we going to continue to get after the ability for us to drive policy so that we can have the right kind of either preventive or preparatory capabilities for our society so that we don't have or can minimize the kind of like damage and destruction that occurred in the Palisades and the Eden fires. I don't know. I'll throw it out to you guys to see where you can go with a question there.
So again, for the models, what we've seen with this new machine learning approach is mostly for weather. It's not for climate. I think it's a safe statement that it's safe to say that in order for it to predict a new event, it has to have seen it in the database. So for climate change, I'm not sure that we have a solution just yet. So I don't know that it would give you the extreme events. I think the extreme event would have to be in the database. So we still use the physics-based approach for long-term for climate modeling.
You got the blue microphone back there.
James
Stand
Coe,
up,
a member.
put it towards your mouth. Tell us your name and if you're a member.
James Coe, I'm a member. And my question is, you showed a little animation, maybe not an animation, but of the carbon monoxide concentration above the fires. And my question is, what is the threshold? I didn't see the numbers of the actual concentration, but what is the threshold of having adverse impacts on health? And then a follow-up would be, I understand that there are other toxic substances that volatilize into the atmosphere above these fires. And how widespread are the adverse effects on health for these other compounds besides the carbon monoxide?
Yeah, so for your first question in terms of the threshold, I don't know the answer to that off the top of my head. But certainly your second point is true. There are all sorts of other things that get lofted into the atmosphere from these fires, especially when you burn through communities where you have, synthetic materials, building materials, fuel, cars, electronics, and those, of course, will transport. But then also, after the fact, you have these environments where there's lots of ash, and that ash is highly toxic. And we don't know, I think we know that stuff can last in the soil for years unless it's properly dealt with after a fire. We're starting to look at some of that in the Pasadena fire, where we've flown our hyperspectral sensor to help determine whether or not we could use that to map some of the toxicity of the ash to help some of the remediation efforts.
Well, stand up.
Actually measure, for example, carbon monoxide concentrations in people's blood, by the way. Is that something that...
I actually don't know that they do that. I don't know.
These guys are firefighters, for goodness sakes.
But I do believe they do it with sometimes the firefighters will wear carbon monoxide detectors when they're fighting fire to collect some health data like that to understand exposure.
We're going to go to the red microphone, and then we're going to take a last question from YouTube.
Cipriani Ivanov again, member. If you're using machine learning to analyze some of this data, how do you prevent the programs from hallucinating additional data? And do you have a way to test for that?
So the way they're analyzing the data, the test is the predictive skill. So the predictive skill is measured in terms of what we call anomaly correlation. So it looks at halfway up in the atmosphere, which is the 500 hectopascal level. It looks at just the ability to predict anomalies. So these predictions are run hundreds and thousands of times to determine whether or not they have predictive skill, and they do. Now, in terms of spurious solutions like you're suggesting, I don't know how often that happens, but I can tell you this. It must not happen very often because the Weather Service and the European Center now have operational versions of the machine learning predictive models. So my guess is it doesn't happen very often. It's a good question, but I don't know the answer.
Okay, last question from our YouTube viewer.
Our last question comes from Will Engel, who asks, what new capabilities will larger satellite constellations and CubeSats provide for Earth sensing? For example, how would having 100 times more sensors in space improve your data?
The more data, the better. And we are using constellations of small satellites to get around the problem of cost. We're using techniques to define what a future constellation to optimize what a future constellation might look like. But I think the short answer is, yeah, we are using small satellites to the largest degree possible right now.
As a footnote, Will Marshall, who is the CEO and founder of Planet, is, if we can finally consummate a date, because we've been back and forth on this for 9 months, they just got $220 million deal, and that's what they do, small sats for Earth observations. And hopefully in the fall, we'll have a talk by Will.
So one comment on that. So for commercial data, which is plentiful now, we do have an issue with calibration. So where in the government, we're very meticulous about calibrating the data, and Landsat, for example, is the gold standard. The private companies don't have, in many cases, a business incentive to go through that process. So we're working with them to kind of iron that out. So I think in the future, we're going to be working with the commercial sector so that their products will be more useful for science.
I thought you mentioned that you were working with Planet.
Yeah.
Yeah, so, all right. Before you go, we have a few presents for you, which you can't really see.
They're right there.
But I'm going to turn this around so you can. Ta-da! So now I can't see. But I know what it is. So the first is a framed copy of the announcement of your talk, signed by all the members of the General Committee, not on their own behalf, but on behalf of all of PSW members and all the viewers who really appreciate your coming here and spending time with us. We also have for you a ribbon. This is the PSW ribbon, and on the side you'll see 3 bars, which are evocative of the symbol for inductance. Why? Because our founder was Joseph Henry. The symbol for inductance is named the Henry, and Joseph Henry studied it. He was the American Faraday. And then we have a copy of not volume 1 anymore. Ran out of copies. Instead, we have volume 17, first edition of the Bulletin of the Philosophical Society of Washington, which is the long-winded name for PSW, sort of like IEEE or ACS. Well, we're PSW. And inside you'll find a collection of the seminal papers. So we have information from the founding, why it was called the Philosophical Society, who founded it, what they thought about scientific discourse. There are a couple of histories that have been written over the years about PSW, a list of Nobel Prize winners who've spoken at PSW meetings, a list of all our Henry speakers, and some paired minutes of talks from the early days on a subject that was spoken about later on as well. For instance, identification of the vector of malaria, with a later talk on how to modify genetically mosquitoes so they can't carry the parasite. So hopefully you'll find it interesting when you're on a long plane trip. You're tired of doing any work of a productive nature. And with that, let me thank you very much.
Thank you.
And
thank you.
Thanks so much. Before you go, we have the usual few housekeeping announcements and talk about our upcoming talks. So the next lecture, number 2510, will be on February 21st, and the speaker will be Robert Smith, professor of history at the University of Alberta, Edmonton. It's really cold there. If you think it's cold here, forget it. He will be talking about the history of the James Webb Space Telescope. He's been writing a book on that for a couple of decades now, so he should be able to tell us a lot about its history. I'm sure he has many interesting political footnotes to inform us of how difficult it was to get that thing to the Lagrange point. The spring schedule is now filled in except for the Joseph Henry lecture. I'm not going to recite all of these. You can go to the web and see them there, or you can take out your iPhone and take a picture. Just note that the 2511th meeting will be on March 7th, and the speaker will be Joanna Drucker. She's Distinguished Research Professor at UCLA, and she'll be speaking about alphabet histories. She's written a number of books about the alphabet. It's quite interesting, a little bit of a departure from many of the others talks that we have. And the 2512th will be on March 21st. Speaker will be David Bennett. He's a research scientist at NASA Goddard, and he'll speaking about detecting exoplanets by gravitational microlensing, a word we probably hadn't heard about until about 10 years ago. And who else should I highlight? In the series of lectures on fusion power that we're having, we've had one by an academic at the UCSD Fusion Materials Research Institute, and our second one will be by Alex Creeley, who is the director of tokamak operations at Commonwealth Fusion Systems. So for those of you who may not know, Commonwealth Fusion Systems is kind of a spin out from MIT, and their approach is based on the development at MIT of high temperature, extremely high magnetic field magnets. So these are magnets in the range of 20 Tesla, and that allows them to condense the tokamak and have a more, theoretically they say, a better control of the plasma that will allow them to make fusion power. I think it'll be an interesting talk. And with that, let's thank our crew for stepping up and helping us produce tonight's show. And with that, I will accept a motion to adjourn the 2509th meeting to the social hour. There are refreshments in the back of the room. And somebody was supposed to take you guys back there. Do I have a motion? Okay. Motion? Second? All in favor? Meeting is adjourned.